Okay, let's talk about the first group. These are known as the alkali metals. These do not include hydrogen. So it starts just under hydrogen with lithium. Alkali metals are soft, silvery, and they're the most reactive of all the metals. They tend to dissolve in water and produce a basic solution. They will also corrode in air rapidly and they'll turn gray. And then they'll react with water to produce hydrogen gas. And then they generally have one valence electron in their outermost shell. So that means their electron configurations are ending on ns1, and they form +1 cations. The whole reason that they form +1 charges is because if all of the metals in group 1 lose their one valence electron, they will be content, and then they will form the nearest noble gas configuration, okay? If you take a look at group 2 are known as the alkaline earth metals. These are also silver colored. They're also reactive, but they are not as reactive as the alkali metals. Some of them have low solubility in water when they combine with a non-metal. They have 2 valence electrons. Their electron configuration ends on ns2. They form +2 cations. The reason they form +2 cations is because they want to desperately lose their 2 outer valence electrons to become a stable configuration like the nearest noble gas. And then you've got group 17. Group 17 are known as the halogens. Halogens are the most reactive elements on the periodic table. And you will have all 3 states of matter present. So you'll notice we have solids, liquids, and gases. And then you've got a rare radioactive solid, astatine, as part of its group. These tend to exist as diatomic molecules, and then they have 7 valence electrons. They end their electron configuration on ns2, np5. They tend to gain 1 valence electron and form a -1 charge so that they can become the configuration of their nearest noble gas, which makes them stable. Last group, noble gases. Noble gases are generally unreactive, but in the lab they have made some compounds with them. All of the noble gases except helium have completely filled S and P subshells. That's because helium only has 2 electrons, so there is no way that helium could have 8 or an octet of valence electrons like all of the other ones do. Generally speaking, their electron configuration ends on ns2, np6. They all have stable octets, meaning 8 valence electrons in their outermost shell except for helium. And then that's the reason why they have no interest in reacting with something else, because they're completely stable. Okay? Okay, let's take a look at the next page. And let's talk about the transition metals. There's a lot to say about the transition metals, but in this class, we're really not going to go into it. They're actually kind of interesting because transition elements can have varying charges, right? So they could have like +1, +2, +3, +4. It just depends. But all of the metals in the middle are mostly hard solids with really high melting and boiling points. They also can form cations with multiple charges. And then those cations can form something called a complex ion. Complex ions are not going to mean anything to you unless you decide to go on and take AP Chem where they talk about it briefly, okay? One thing that's really important about transition metals is that a lot of the transition metal compounds will have recognizable colors, and a lot of these ions will have recognizable colors when they're dissolved in water. So like some of the different irons, like iron 2, iron 3, or some of the other metals will have distinct colors when they're dissolved in water. Like they might be yellow, blue, green. So that's something that's important to know. And the reason why is because their electrons are placed in the inner d orbital. So they're closer to the nucleus. And that type of interaction leads to these distinct colors. Okay? Okay. Now, let's take a look at the last pages. On the last couple pages of this section, all they're doing is they're kind of referring back to the electron configurations that we learned in the previous section. And they're just showing you that you can refer to some of the regions on the periodic table as blocks. So for instance, this green region, those are your S subshells. They refer to that as your S block. Over on the right-hand side, this white region, these would be the P subshells. That's your P block. In the middle, D subshells, that's your D block. And then underneath at the bottom, this is the F subshell. So that would be your F block. Okay. And then on the next page, they show you that, where is it? Right here. They show you that, generally speaking, at the top, this is what we're ending on for that particular group for their electroconfigurations. So this first one ends on S1, meaning you have one valence electron, S2, two valence electrons, and then they just kind of like carry it out with the Ds and the Ps. Okay? And that's all we need to talk